let's talk about congruence of these triangles. So our definition is about congruence of sides of the triangles. So for instance here, ABC is going to be congruent to DEF under the correspondence A corresponds with D, B corresponds with E, and C corresponds with F. That congruence is determined by looking at the three sides and the three angles. Right? So in some sense we're saying take a ruler, check that it matches, checking the various sides here, checking that it matches, and then similarly, maybe with my little protractor here, this tiny little protractor, I measure the angles and check that the angles correspond to each other and are congruent in that way. Now that's a fine definition. It's the one that we've been using so far. And of course, we have a number of theorems that say we only need to check 3 of these 6 things. Right? We only need, for instance, because of side angle side, we only need to check AB matches up with DE. We need to check that AC matches up with DF, and then we check the angle in A matches up with the angle in D. Right? That's a great way of checking congruence of triangles. But there's another way. Right? There's another way, which is to pick up my triangle and put it on top of it. And that is a way of verifying congruence. Here I'm going to take this one. This guy, I made it so I'm going to have to flip him over and make him match like so. Right? So these triangles are congruent, and we've checked it by this method of picking up the triangle and putting it on top of the other one. So our goal here is to make sense of what do we mean by that, picking up a triangle and putting it on top of the other one. That's not a well-defined mathematical idea, so we're going to put some theory to make it into a well-defined mathematical idea. Okay, let's think about Pappus's proof of the isosceles triangle theorem. Right, if you remember our theorem, we showed that if ABC is an isosceles triangle, then the angle in B is congruent to the angle in C. And the idea of Pappus's proof was just a relabeling of the triangle, to say that triangle ABC is congruent to triangle ACB, and for that we use side angle side. Okay, let's think about another way of interpreting the exact same proof. In some sense, what Pappus is saying is that we are taking the triangle and flipping it over. Right? So if A stays where it was, but C moves over here to the left, and B moves over here to the right. So we see this kind of flipping. Our goal is to make sense out of that also. And there's some ideas that we have that are intuitively obvious. So here I have an equilateral triangle, or my best attempt at making one. I have 2 copies of it actually, one to stay on the table as a reference, and this one that I'm going to move around. So we can ask the question, what are the symmetries of this triangle? Well, we can imagine this triangle like this, but we can also imagine rotating it. We can imagine rotating it some more. Or we can do some more, some flipping, right? We can flip it over like this. We can flip it over like that. And we can flip it over like this. So if we're paying attention here, if we include the symmetry of actually doing nothing, we imagine having 6 symmetries here. Right? The rotation through angle 0. Then we have this one that's rotation by 120 degrees. Rotation by either think of it as 240 degrees or minus 120 degrees. And then we have, right, if we rotate one more time, we come back to where we started. And then we have these three flips. So that gives us 6 symmetries. Now, it's intuitively very clear when I'm manipulating an equilateral triangle, but we need to make sense out of this as a rigorous mathematical idea. So that's one of the things we're going to be working on in this section, in this module. And now finally, here's another object with a lot of symmetries. Here I have a square, or my best attempt at a square. And this square, we see it has a different collection of symmetries from my equilateral triangle. Right, the equilateral triangle, there's this threeness to its symmetries. So this guy has 6 symmetries. This guy has a 4ness to it, whatever that means. Right, so this one, there are going to be 8 symmetries analogously to the equilateral triangle that had 6. Right, this guy, we can do nothing. That's the first symmetry. We can rotate it 90 degrees, a second symmetry. We can rotate it 180 degrees. That's another symmetry. We can rotate it 270 degrees. That's now our 4th symmetry. And now what we can do is we can imagine taking a line that bisects my square, so for instance this vertical line here, and use that to give us a flip. Right, so the flip is another symmetry. Here is another symmetry. And then we can flip also along each of the 2 diagonals. So this gives us 8 symmetries. So an interesting thing is the symmetries of these objects are a way of telling them apart. Right? The square is different from the equilateral triangle because they have different numbers of symmetries. But also my isosceles triangle is different from the equilateral triangle because this guy does not have any of the rotational symmetries. He just has one of the flip symmetries. So the symmetries know something about the triangle or about the shape in general. So we're going to dig a little bit deeper into that idea in this module. At the beginning of this video, I showed a picture from the math department library of the portraits of Felix Klein and Emmy Noether. And they are both important for us today. Felix Klein especially, because Felix Klein proposed in the 1870s this idea that to understand geometry, you need to understand the symmetries of that geometry. So that's a general principle, and it's a very influential one. Meanwhile, Emmy Noether, who's a more recent mathematician, I believe she died in the early to mid-30s, she proved some important results about the correspondence between symmetries on the one hand and conserved quantities on the other hand. So in a physical system, which is one that many of us are interested in, the things like conservation of energy corresponds to things like or conservation of momentum correspond to translation invariance of the laws of physics. So in that sense, symmetries have an important connection to topics in physics. Anyway, we're going to focus on transformations purely in a geometric context. So let's start by building up some language and machinery so that we can talk about the idea of a transformation of the plane and of symmetries. Okay, so we're going to write P in this blackboard bold to indicate the set of points in the plane. And then we're going to say that a map of the plane is a function from the plane to itself. So a natural thing to do if you think in coordinates, or in Cartesian geometry, is to identify the plane with R2, and then we can think of this map F as being a map or a function from R2 to R2. Right, quite often we use the word map if we're talking about a function where the domain and the codomain are the same thing. Okay, we're going to restrict our attention from arbitrary maps, and instead we're going to want invertible maps. What we mean by that is we want to be able to undo the operation. Right, all the operations I did at the board where I move a triangle onto the other triangle, well, I can move the triangle back to where I took it from. So in that sense, we want this operation to be one we can undo. So in other words, we want the inverse function, which we write by this f to the minus 1, we want that to exist. Equivalently, this means we want our map f to be a bijection from the plane to itself. So that gives us a definition here. A transformation of the plane is a bijective map f from the plane to itself. It's maybe been a little while since you've heard this word bijective, so let's do a brief amount of Math 305 review. So the first bit of technical jargon we're going to review is calling a function one-to-one or injective. So we say a function f, or in this case a map f, is one-to-one or injective if for any two distinct inputs we get two distinct outputs. Now quite often we word this, right, so the first way I worded it here is the one that corresponds to the words that I wrote up here. For any two distinct inputs, so if p is different from q, we get two distinct outputs. So f of p is different from f of q. That's great. It's often quite useful to do this using the contrapositive. So the contrapositive here says that if f of p equals f of q, then actually the only way for that to be true is if p equals q. And so remember, the contrapositive is the statement, if it rains while you're watching this video, when you go outside, the sidewalk will be wet. The contrapositive is, if the sidewalk is dry when you go out, then it did not rain while you were watching the video. Okay, so here are some examples. If I look at the function f of xy is given by x squared y, this guy is not injective. And the reason, all we have to do is find two distinct points in the domain that map to the same point in the codomain. So here I'm going to notice that f of, let's say, 1, 3, that's going to be, that's 1 squared 3, that's just 1, 3. And then meanwhile, f of negative 1, 3, that gives me negative 1 squared 3, so that's that same point. Right, so two different inputs give me the same output, therefore it's not injective. Here's an example that is injective, and that one's injective because we can just go ahead and show it. So here, let's say, suppose f of xy is equal to f of uv. Right, so this is playing the role of my p and q from the previous slide. Then what this means is x cubed comma y cubed equals u cubed comma v cubed. So that gives us that x cubed equals u cubed and y cubed equals v cubed. And now we can just take cube roots. And hence, the point xy is the same as the point uv. And that shows that this is injective. Okay, we'll say that a map is a surjection, or that it is onto, or that it is surjective. Right? So for both injection, injective, surjection, surjective, this is the noun form, and this guy is the adjective form. Okay, so we say that a function f is onto or surjective if it hits every possible value in the codomain. So in other words, in this case of a map from the plane to itself, we're saying for every point x comma y in the plane, there exists a coordinate uv, so that f of uv is equal to x comma y. So here are some examples that are surjective. Well, this first one is surjective. That one is a little exercise to prove, and I'm going to assign it in the homework. I mean, the key ingredient is that x and y are completely separate from each other. So this is going to be surjective if and only if this first coordinate function there is surjective as a map from the real numbers to the real numbers. And this guy you can show is surjective by using a combination of the intermediate value theorem and the fact that the limit as x goes to infinity of x cubed minus x is plus infinity, and the limit as x goes to negative infinity of x cubed minus x is negative infinity. So using those two ingredients, you'll be able to do the homework problem I've posted. Now, a different example that is not surjective is this function f of xy is given in coordinates with e to the x comma y. So here, why is that not surjective? Let me give you a brief moment to think about it. The reason is e to the x can never hit a negative value, right? So for every x, e to the x is a positive number, whatever x is. So this means there does not exist any x and y, or maybe I should use u and v to match my previous notation. And I get to choose my favorite negative number. Let's say -3, comma, anything, 0. Right? -3 is not e to any number u, so it's impossible to obtain this as a point that is hit by the values of my function, by the image of my function. Okay, if I have a map that is both injective and surjective, we say it is bijective. So the two properties together we say is bijective. And something you may remember from Math 305, a map F is bijective if and only if there exists an inverse function that we write as f with this power -1 here. And that inverse function is going to reverse the domain and the codomain so that f composed with f inverse is the identity, and f inverse composed with f is the identity. In the case of a map, this is arguably a little bit confusing, but if we have a general function, right, let's say I have sets here A and B, and I think of a general function from A to B, we can think of it as giving us a recipe for sending points. Something like that is an example of a bijection from A to B, and then F inverse is what we get by reversing the direction of those arrows. So that's the picture I want you to have in mind for a bijection. It is a map that you can undo basically by reversing the direction of the arrows. So an example you know very well from, I guess, from calculus or pre-calculus is the function. So here I'm thinking of a function from R to R that says f of x is x cubed. In that case, the inverse function is the cube root. That's a well-defined function. Everything's perfect. Now, there are many functions we think about in calculus, and I have a few examples here, right? The square root function, arctan, the natural log. Those functions are inverse functions of things that are not bijections. So instead what you have to do in those cases is you have to chop up the domain and or the codomain in order to get a bijection between this restricted domain and or restricted codomain, and then are able to make sense out of it. Right? So the square root function, what we're saying is if I define g of x to be x squared, if I look at g from R to R, it's not a bijection. But if I look at it instead from a smaller domain to a smaller codomain, this is a bijection. So the square root is defined for the non-negative real numbers. Right? It's defined there, and it takes values between 0 and plus infinity, because this idea of the inverse function requires the square root function to be a bijection, and it only is if we consider it in this restricted sense. Okay, that's great. We have some understanding of bijections in the context of functions from R to R. Let's think about some geometric examples. So here I have chosen two of them to highlight, but we'll see many, many more as we continue in this section. So here's something that's called a shear transformation. Okay, a shear transformation, we can think about it very nicely as this kind of disastrous knocking of a pile over, right? If I take my pile of papers and magazines and whatever else, I can push it over like so. And at some point it's going to fall over because, you know, we have gravity and stuff. But right, this transformation where I keep each layer of my pile at the same height, but I push over a different amount depending on how high up I am in the pile. So this top guy got pushed over an awful lot. The guy at the bottom didn't get pushed over at all. And the people in the middle got pushed over sort of a medium amount. And that's an example of what's called a shear transformation. Obviously, this right here is a transformation I did in space, but we can do the same thing down a dimension, right? If you imagine just looking at the cross-section of this pile. Let's go ahead and check that this shear transformation is actually a bijection from the plane to itself. So I want to think of it as a function from R2 to R2. This f of xy is x plus y comma y. I'm going to check it's a bijection. And for this kind of thing, there are basically two methods. So I will outline them. We will do one of them. The first method is the direct one based on the definition. So for this, we can check, first of all, that f is injective, and check f is surjective. Right? That's a fantastic way of verifying this. Instead, we're going to look at something else. We're going to say we can show that it's a bijection by constructing F inverse. And so I should emphasize this is or. Construct F inverse and show, or I should say, and verify F composed with F inverse is the identity, and F inverse composed with F is the identity. Okay, so let's go ahead and construct this. So the idea of how we do this is we say f of xy is the point, let's say, x prime, y prime. Then we want f inverse of x prime, y prime equals xy. Okay, that looks silly worded like that, but let's go ahead and figure out what this means. And so if I take this statement right here and expand what f of xy means, and so f of xy is x plus y comma y, I want that equal to x prime, y prime. So in other words, I can think of this as a system of equations where I have x prime is equal to x plus y, and y prime is equal to just y itself. And what we want to do is we want to rearrange this where we solve for x and y in terms of x prime and y prime. Good, so let's go ahead and solve it. Our first equation here gives that x is x prime minus y. Our second equation says that y equals y prime. So we can go ahead and substitute here to say x is x prime minus y prime and y equals y prime. So now we go back to this statement right here, and that allows us to say then that f inverse of x prime, y prime is given by what we just calculated. So that gives me x prime minus y prime, comma, y prime. So now we've constructed the candidate for f inverse, and we need to check, we need to check that f composed with f inverse of x prime, y prime equals x prime, y prime, and that f inverse composed with f of x comma y is x comma y. So those are the two things we need to check. I'm going to check one of them. The other one is basically a very similar calculation, so I'm not going to waste our time doing it. But if you have a problem in which what you want to calculate, you should check both, or at least say that you could check both and indicate how it works. So let's go ahead and calculate the first of those two. Right, so that's f inverse of x prime, y prime. We calculate that first, and that's going to give me x prime minus y prime, comma, y prime. But now remember, the output from f here is going to give me, get the x coordinate that you feed it, plus its y coordinate, comma, the y coordinate. So that's x prime, y prime. So that's indeed the identity as we wanted. Similarly, you know what, I think I lied. Let's go ahead and just do it. And remember, f inverse takes its x coordinate and subtracts the y coordinate. So that gives me x plus y minus y, and then the y coordinate doesn't change. So this gives me x, y. So indeed, this works for any x prime, y prime, any xy, and thus f is a bijection with inverse that we calculated. Okay, how do we visualize transformations? To visualize a transformation is very difficult because the transformation, you can think of it as a function from R2 to R2. Now, if you think about a function from R to R, to visualize it as a graph, you want to draw a picture that's in a two-dimensional space. You have one dimension for the domain and one dimension for the codomain. If you have a function from R2 to R, you now have a surface sitting inside of three-dimensional space. So now a function from R2 to R2, if you want to make its graph, you're going to have some kind of two-dimensional surface sitting inside of a four-dimensional space. That's incredibly hard to visualize. So instead, what we can do is we can look at how it transforms pictures that we know. So the idea is we take a picture we know, and then we apply the transformation to it and see what happens. So we could do this by hand, in principle. That's a fairly tedious amount of work. Or we can use a tool like Mathematica. So let's now take a quick look at how to do it in Mathematica. And as a reminder for hopefully some of you, and if not, just as information for you, the university has a site license to Mathematica, so you can install Mathematica on your home computer. Otherwise, there's this fantastic product that Wolfram, so those are the manufacturers of Mathematica, they have this thing called WolframCloud, and you can use it on a free tier of account. It doesn't have as many features as the full-fledged Mathematica, but I have a link to my WolframCloud file that I have in Blackboard, and I'll put a link also in the description of this video, and you can take a look at it and mess around with it if you like. Okay, here's my Mathematica worksheet. I have loaded some things, and I've constructed a dartboard image that we're going to use as our starting image. So on the left here, so here I have this face of a mandrill. That's the image we're going to apply our transformation to, or our map. And down here I have this sort of dartboard picture that we're going to apply the map to. Okay, my first map that I have is, I'm saying f of xy is x plus sine y comma y squared. So this is a map that is not invertible, right? This thing is not surjective onto R2 because this y squared is always going to be non-negative. Right? So we aren't going to hit every point, and you see that here. This is what this sort of black hole down here represents, and our image looks very strange. Okay, so we're going to leave these kind of bad maps aside, and let's look instead at, let's start with our shear transformation that we talked about. And so here I have changed my function, so now f of xy has coordinates x plus y comma y. I'm going to evaluate my notebook, and we see here it's doing the thing where it slid over my picture, right? That was like my stack of papers that I slid over, except here it's this mandrill that's getting shoved over. And down here in our dartboard image, we see it getting shoved over as well. And you'll notice that this is not an isometry, right? Because if it were an isometry, the circle would stay a circle, but instead it gets deformed into an ellipse. Right? This point right here on the right and this point here on the left are the same distance apart as this point on the top and that point on the bottom, but their images are here, and you see that the distance between the images is not the same. I guess I should have said that point, that pair of points, right? Those two right there. So this is not an isometry. However, there are isometries that we could do. We can do a translation where we just slide the picture over in some direction or other. And so there I've just shifted my picture to the right. We don't see anymore what's happening just because the picture is half off of my view screen, but we just moved everything over to the right by 1 unit, and that is indeed an isometry. It preserves the distances. We can look at something more exciting, like a reflection. Let's say I'm going to flip it around the x-axis. And here I've just turned everything upside down. So that is a reflection about the x-axis. And that's an example of an isometry. We can do rotations. So let's do a simple rotation, a rotation by 180 degrees. Right, that's at the level of the mandrel. He was symmetric enough, it's hard to tell the difference. But here you can see the difference because the letters now, or I should say the numbers, are written the correct way around, they're just upside down. Whereas in the previous incarnation, we had the mirror image. So our Arabic numerals here remembered whether we have a rotation or a reflection. Okay, and then of course we can do any number of things like this. Let me there's some built-in ones in Mathematica. So let's say I can make it a rotation. And see there, I rotated by pi over 6 in the positive direction. So in other words, in the counterclockwise direction. So we can visualize these transformations very nicely using Mathematica. And like I said, I have a link to my WolframCloud that does this. In the WolframCloud one, I've commented out the mandrel stuff because the amount of computation power required to do the image processing on this is more than you reliably get on the free account. However, my little dartboard image here works fine. So this brings us back to that photo that I started the video with. Klein's idea from the 1870s is that geometry is encoded by its symmetries. So if we understand the symmetries of a geometric object, we understand the object in some sense. So we want to make a sense out of what is a symmetry that's meaningful for a geometric construction. So an important class of transformations we're going to look at are these so-called isometries. So isometry, you should think of it, right? Iso means the same. It's a Greek prefix for the same. And metry is about measuring things, right? If you think about meters or a thermometer, thermometer is for measuring temperature, thermo. Here, isometry means the same measurement. So in this case, the same distance. So maybe the meter idea is more relevant. So an isometry is a transformation of the plane with the property that if you give me 2 points x, y, and then I look at their images x prime and y prime, then the segment xy is congruent to the segment x prime, y prime. So in other words, this is a transformation of the plane that preserves distances. Now that's not the only kind of transformation that's meaningful or relevant in mathematics. So depending on the kind of problems you're interested in, important ones are area-preserving transformations. So that's going to include all the isometries, but it also includes our shear transformations. Another class that's important is something called a conformal transformation. So here we're thinking of it as preserving shapes. So that one is angle preserving. So there are many examples of these. Obviously the isometries are going to have this property, but also inversion through a circle, which we will see a little bit later on in the course. And then there's something that, depending on the author, is called either a similitude, a similarity, or a similarity transformation. This is something where instead of it preserving distances, it scales all the distances by a uniform amount. So for instance, to give an idea of a similarity transformation, that I just did to the screen is an example of a similarity transformation. And I just scaled all the distances by the same amount. An important theorem is that isometries preserve basically everything that we care about in geometry. So I'm going to assume here that I have an isometry T of the plane, and I have 3 points A, B, and C. And I'm going to call A prime the image of A, B prime the image of B, and C prime the image of C. We're going to use this kind of prime notation quite often in our continuing work on transformations. So the first thing is, if A, B, and C are on the same line, so if they're collinear, and they are in the order A, B, C, so B is between A and C, then their images also are on a line, and they have A prime, B prime, C prime in that order on the line. So B prime is between A prime and C prime. Okay, if they are not on a line, and we want to talk about an angle here, the angle ABC is congruent to the angle A prime, B prime, C prime. So an isometry is an example of a conformal transformation. It preserves angles. And then finally, it's going to send triangles. So if ABC is a triangle, its image, A prime, B prime, C prime, first of all, will be a triangle. And second of all, is going to be a triangle congruent to my original triangle. Okay, and then I'm going to ask you to check this on the homework using one of our congruence theorems that we already know. I've worded this as an if statement, right? If, for instance, if this is a triangle, then that. But it turns out that this is actually an if and only if theorem, basically automatically. So I'll have you think about that a little bit. Pause the video if you like, and think about it for a second. Okay, the key reason that this works is something I will have you check, is that the inverse of an isometry is also an isometry. And because of that, I can apply my theorem where I think of A, B, and C as being the output points, and A prime, B prime, C prime as the input points for the mapping T inverse. And then that allows me to flip the direction of implications for each one of my 3 statements that I have here. And that's why this is an if and only if statement. Let's introduce a very important example of a transformation of an isometry, which is something called reflection about a line or reflection across a line. So we let L be a line, and we're going to define a transformation R, that's the reflection about the line L, where we say that if the point is incident to L, it doesn't move. If the point is not incident to the line, then we're going to construct a point P prime so that L is the perpendicular bisector of PP prime. So the picture to imagine is I have a line L here. If I put a point here P on the line, that's going to be the same as its image. Right? P and P prime are the same if I'm on the line. But otherwise, if I'm here, and if that's P, then we have our point P prime on the opposite side of the line L, and we have this little segment here that is perpendicular to the line L, and I want it to go the same distance on the right as on the left. Right? So in other words, I'm making L be the perpendicular bisector of the segment PP prime. Okay, on the homework, you're going to check that R is well defined and that it's an isometry. And so a nice fact is that reflection about a line is something that's built in already to GeoGebra. So here, let's go ahead and demonstrate reflection using GeoGebra. So I'm going to start here with, I have a point A and a line BC. Then I have here this tool, which is reflect about line. So I click the point first, and then the line, and then it constructs me a new point. Here, for whatever reason, it named it A prime. I kind of like that, actually. Right, and as I move my point closer to the line, I see that, and I can move through the line. So you should think of this is called a reflection. GeoGebra says reflection about the line. Some people say across the line. And of course, I can have fun with for instance, a triangle, and I can reflect it about the line. And we can get funny looking things, right, where maybe some of the points are on one side of the line and some points are on the other side. So these are, this is an example of GeoGebra and reflections being a built-in object in GeoGebra. Okay, so happy mathing. I hope you enjoyed the video. See you on the next one.